Jai Hind students, I hope you all are keeping very well, and I'm very sure that you are studying on a consistent basis, right students? So today we are going to discuss a very interesting topic, and the topic is related to the color coding of a carbon resistor. Now resistors, as you are aware, it's a very important electrical component. It's used in almost all the electronic circuits, right? And one thing I must mention is that why we make use of carbon resistors? Why not some other resistor? The answer is carbon is readily available. So carbon resistor, since it is readily available, so it is very economical, right? You can get quite a number of resistors even for 2 rupees from an electrical shop, right? So it's so economical. And second is it offers high resistance, and third is it can withstand high electrical pulses. So these are the 3 reasons why carbon resistors are preferred. So we make use of some color coding, and noting down the colors of the concentric rings or the bands, we can identify the value of resistance of that given resistor. So in today's session, we are going to discuss the color coding of carbon resistances. Right students? So a resistor basically, a carbon resistor basically, it's in a cylindrical form, a small one, it's very portable, right? So that is another advantage of using carbon resistor. And it normally contains 4 concentric colored bands. First 3 on one side and the 4th one on the other extreme. The 4th one on the other extreme. The 4th band, it may be either of gold color or silver color, or it may be totally absent. Right? So we'll discuss its significance. So in the color coding, you need to remember that there are 4 concentric colored rings or colored bands. So by following a certain rule, we need to, or rather we can easily identify the value of the resistance offered by that carbon resistor, right? So what's the rule basically? So the color of the first 2 bands, that will represent the value of first 2 significant figures of the value of resistance in ohm. The color of the 3rd band, that will represent the decimal multiplier, 10 raised to power. So that will represent decimal multiplier. And the 4th band, which may be either gold, silver or no color at all, it represents the tolerance of the resistance, right? So basically, a resistor is like this, a carbon resistor is like this. It consists of 4 concentric colored bands, 3 on one side and the 4th one is on the other extreme, right? So the first 2 colors, 1 and 2, the first 2 bands, it represents the first 2 significant figures of the value of resistance in ohm, right? The color of the 3rd band, it represents the decimal multiplier. And the color of the 4th band, which I have already stated, it may be either gold or silver, it represents the tolerance value of the resistance. It may be either 5%, 10% or 20%. So before we proceed with these 2 examples, we need to get along with this table, right? So this is for ring A or B. And first 2 significant figures, so we are supposed to write from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 3rd one, this is suppose A, this is ring B, this is C, and this is suppose B. So C, that represents decimal multiplier, that is 10 is to power 0, 10 is to power 1, 10 is to power 2, 10 is to power 3, 10 is to power 4, and so on, till 10 is to power 9, right? And D, which I have stated, it can either be gold, silver or no color. For gold, it is 5%, for silver it is 10%, and In case the fourth band is absent, then it is 20%. And this is basically the tolerance. Right? So, the first two concentric colored bands that represent the value of first two significant figures or the significant digits of the value of resistance in ohm. Third band, the color of the third band, that represents decimal multiplier. And the fourth one, which may be either gold, silver or no color at all, it represents tolerance. It may be either 5%, 10% or 20%. Now students, a sequence of colors, that is important, that you need to remember. First one is black. Next is brown. Red. Then it's orange. Then it's yellow. Then it's green. Then it's blue. Then it's violet. Grey, and then white. So these are the sequence of colors which you need to remember so as to obtain the value of resistance in ohm by just observing the colors of the concentric bands. Right, students? So how to remember this? How to remember this? There is a very interesting thing by which you can easily remember this sequence of colors. Let's consider the first alphabet of each color, right? So what do you get is B, then again B, then R, then O, then it's Y, then G, then it's B, then V, then again G, and then W. We can extend this as well, GSN. The starting letter of gold is G, silver is S, and no color N. So over here write GSN. Now you need to remember this sequence. So B.B. Roy, it's the name of a person, B.B. Roy of Great Britain. Of Great Britain. He resides in Great Britain. Has a very good wife. Has a very good wife. And wives, students, they are fond of jewelry. So has a very good wife wearing gold, silver necklace. I hope simply by remembering this particular statement, you can remember this sequence of colors. I repeat, students, it's a very interesting one. It's quite easy to remember this thing. B.B. Roy of Great Britain has a very good wife wearing gold, silver necklace. So by using this, you can remember the sequence, right? Black, brown, red, orange, yellow, green, blue, violet, grey, white. Then for the D, tolerance value, which gives tolerance, it's gold, silver or no color. Clear, students? Interesting now? So again I repeat, B.B. Roy, that's the name of a person, of Great Britain, has a very good wife wearing gold, silver necklace. So this is how I am very hopeful that you will be easily able to remember the sequence of colors, right? And I repeat again, the colors of the first two bands that will represent the significant figures of the value of resistance in ohm. The color of the third band, which I am represented by C, that will represent the decimal multiplier. And students, the fourth color, which may be absent as well. It may be either of gold color, silver or totally absent. It represents tolerance value. Right? So now let's make use of this chart to answer those two questions. Okay. Let's consider on the first one. Let's consider on this question. How will you represent a resistance of 3700 ohm plus minus 10%? Now 3700, now look, it can be written as 3700 ohm plus minus 10%. It can be written as 37 into 10 raised to the 2 ohm plus minus 10%. So we are supposed to write the sequence of colors. So what will be the first color? What will be the first color? 3. It corresponds to orange. The color of the first band must be that of orange. 7. It corresponds to violet color. Right? 10 raised to the 2. Third one, it represents the decimal multiplier. It corresponds to red color. So this one is red. And this is tolerance. 10% is the tolerance, which is silver. So sequence of colors must be like this. There is a carbon resistor. These are the 3 concentric colored bands I am talking about on one side, and the 4th one is on the other extreme. Right? This is A, this is B, this is C, this is D. This one is orange. First one is orange. The second one is violet. Third one is red, and tolerance is 10%, so it will represent silver. So this is the sequence of colors. This is the sequence of colors. Right? So the first 2 digits, these are the significant figures of the value of resistance in ohm. Its value will be given by the colors of the first 2 bands. This is the decimal multiplier. It is represented by the color of the 3rd band, right, which is C. And this is the tolerance, which represents or which is represented by the either gold, silver or no color at all, which is represented by the 4th band, that is D. So I hope it's pretty simple. It's absolutely clear. Okay, let's try the other one as well. Right? Let's consider this question. Okay, here the color sequence is given. In this question, the color sequence is given and we are supposed to find out the value of resistance in ohm. So how to proceed like? Look, first one is yellow. So, first one is yellow. It corresponds to the value of 4. So the value of resistance would be 4. This is the first significant digit, right? The color of the second band is violet. So violet corresponds to 7. So this is the second significant digit of the value of resistance in ohm, right? Then the color of the third band, which is brown, that represents decimal multiplier, multiplied by 10 raised to the power something. So that is brown. Brown, it is 10 raised to the power 1. This is the decimal multiplier. Plus minus, this will give tolerance. Gold indicates a tolerance value of 5%. So it is 5%. This will be in ohm. So it may be written as 470 ohm plus minus 5%. So that's the answer. Clear, students? I hope you have understood this concept of color coding. It's very simple. Just remember this sentence. B.B. Roy of Great Britain has a very good wife wearing gold-silver necklace. And that will solve your purpose. By simply remembering this sentence, we can do any questions related to this particular topic. Right? So, this color coding in carbon resistances is over. So, in this session, we can continue with one more topic. It's an interesting one. I'm talking about the phenomena of superconductivity. Now look, students, we all are aware how the resistance get affected with the increase or decrease in the temperature in the case of a conductor, right? In the case of a conductor, the resistance increases with the increase in the temperature, and the resistance of a conductor decreases with the decrease in the temperature. So superconductivity phenomena is based on this concept only. The phenomenon of superconductivity is based on this phenomenon only. So let's discuss more about superconductivity. Superconductivity. We have discussed the resistivity and hence resistance increases with the increase in the temperature. In case of a conductor, we are talking of conductor, right? No doubt regarding this. We have proved it mathematically as well. So from this we can conclude that resistivity and hence resistance of a conductor decreases with the decrease in the temperature. Right? This is a known fact. In case of a conductor, the resistance increases with the increase in the temperature, and therefore the resistance of the conductor will also decrease with the decrease in the temperature. So students, just imagine a case where the temperature of the conductor is kept decreasing gradually. So what happens? The resistance or resistivity of that conductor will also keep on decreasing along with the decrease in the temperature. So a stage will come when at a particular very low temperature the resistivity or resistance of that conductor might become zero. It is in that case the conductor is said to have become a superconductor. And this striking phenomenon is known as superconductivity. Actually, this phenomenon was first studied by Camillin Ohms of Netherlands way back in 1911. What he did was, he studied the variation of resistivity of solid mercury with that of temperature. So basically, he studied the variation of solid mercury, resistivity of solid mercury with temperature. Capital T represents the temperature in the absolute scale or Kelvin scale. So this is the temperature in the absolute scale in Kelvin, and this is supposed the resistivity. So this was a known fact. When the temperature is decreased, the resistivity of the conductor will also start decreasing. So initially, what he found was experimentally, he found that with the decrease in the temperature, the resistivity of the solid mercury also decreases in a expected or normal manner. But at a particular temperature, and in the case of solid mercury, that temperature was found to be 4.2 Kelvin. It's very, very low temperature, right? So, at a particular temperature, which for solid mercury was 4.2 Kelvin, the resistivity or resistance suddenly disappears from the graph. It's clear that at 4.2 Kelvin, over here the resistivity is 0. Resistivity is 0 means resistance becomes 0. So this temperature, 4.2 Kelvin, it is known as the critical temperature of solid mercury. For different substances, the critical temperature would be different. It will depend upon the nature of material of the substance under consideration, right? So, what he studied was, he studied the variation of resistivity of solid mercury with temperature. So, Camillin Ohms, while experimentally studying this, found that initially the resistivity of solid mercury decreases with the decrease in the temperature. But at a particular temperature of 4.2 Kelvin, the resistivity abruptly becomes 0. So this temperature at which the resistivity and hence resistance of the solid mercury becomes 0 is known as the critical temperature. This is the critical temperature of solid mercury. So at this temperature, solid mercury has become a superconductor. Means it is offering no resistance, it is offering no resistivity at all. So this striking phenomena is known as superconductivity. Now imagine what happens at such low temperature. Just imagine the temperature, I am talking about minus 269 point something temperature in degrees Celsius. Kelvin scale, you are aware, it's represented by T plus 273, isn't it? So substitute the value of capital T as 4.2, so you will get the temperature in degrees Celsius. It will come out to be about minus 269 point something degrees Celsius. So we are talking about extremely low temperature which can't be achieved in our daily life, isn't it? So it is only at that extreme low temperature that this phenomenon of superconductivity can be realized. So what happens at such low temperature? How the resistance becomes zero? Let's theoretically interpret it. I have told you, students, with the increase in the temperature, the positive ion starts vibrating more vigorously and with greater amplitude. Consider the reverse scenario. Now with the decrease in the temperature, the vibrations will be very small and the amplitude will be extremely small. Almost the positive ions, its vibration will cease to exist, isn't it? It will almost cease. It will almost stop. So that the electrons, while drifting, they won't experience any appreciable resistance, or they will experience negligible resistance. Actually, at such low temperature, the electrons moves inside the conductor in the form of mutually coherent cloud. At such low temperature, the electrons moves in the form of mutually coherent cloud. So as a result, the resistivity or the resistance offered by the superconductor at such low temperature is almost zero. And at such scenario, the conductor is said to have become a superconductor, offering no resistance at all. So if it doesn't offer any resistance, so students, no energy is required to overcome the resistance, so it can save us from the energy losses during transmission. So there comes the application of superconductivity, right? If we are able to actually realize this phenomena at much higher temperature, then it can bring revolution. It indeed will bring a revolution. In such a scenario, during the energy transmission, there won't be any energy loss during the electrical energy transmission by using superconducting cables. And second, using this concept, we can make super fast computers. At present, we are having super fast computers, but using superconductors, we can have supercomputers which are at greater speed, which works at greater speed, right? So these are some of the applications of superconductivity. So it is basically based on the fact that the resistance of a conductor decreases with the decrease in the temperature. So if you keep on decreasing the temperature, the resistance will also keep on decreasing. So at a particular temperature, which is very low, the resistivity or resistance of that particular conductor becomes zero. That temperature will be known as the critical temperature of that particular conductor. So that's superconductivity for you, right? So I hope you have understood this concept, and it's a simple one. So for this session, let's conclude with only these two topics. One is the color coding of carbon resistors, and the second one we have discussed is superconductivity. So we'll continue in the next session then. Till then, do take very good care of yourself, and bye-bye.